everyone. In today's video, we're going to be talking about atomic theory and structure. So what theories we look at when we talk about the atom itself and what structure we theorize that the atom itself has. At the end of this video, we should be able to list the basic postulates of Dalton's atomic theory. We should be able to recall the experiments and scientists that were involved in the discovery of the electron and the neutron and the proton and the overall nuclear model of the atom. And then we're going to look at those three subatomic particles and look at their relative sizes and masses. Then we're going to be able to convert between the different subatomic particles when we have our charge or our atomic mass. And then lastly, we'll do atomic, and then lastly, we are going to be able to perform isotopic abundance calculations. We're going to start with a little bit of history. So the first thing that really led to our modern atomic theory came in 430 BC when Democritus, a Greek philosopher, first proposed the idea of the atom. Or atomus. And it was this thing, this indivisible particle that all of the material world is made of. And if we had different materials, the difference in their atoms was their shape. So different material were made up of different shaped atoms. Next, in 1788, much longer, we have Antoine Lavoisier. And he came up with the law of conservation of mass. So within the law of conservation of mass, matter can neither be created nor destroyed. Okay, and then next, 1794, we have Joseph Prost. And he came up with the law of constant composition. So with our law of constant composition, if we have a pure compound, it will always have the same atoms in the same ratios. Okay, so they will be the same atoms that make them up in order to be a specific compound. And then 1808, John Dalton came up with the idea of the law of multiple proportions. And here, if we have two elements, A and B, if they form more than one compound, the masses of A that can combine with masses of B are going to be in small whole number ratios. So basically, atoms A and B will combine in small whole number ratios to make compounds. The next major advance in atomic theory is John Dalton's atomic theory. So this is one of the first real working atomic theories that were developed. And he said that each element is composed of extremely small particles called atoms. So any element within our periodic table, they are made of atoms. Those atoms themselves are going to be identical to each other, but the atoms of one element are going to be completely different from atoms of another element. If we have an atom of an element, it cannot be changed into the atom of a different element. So no changing lead into gold, unfortunately. All our alchemists are wrong. And then we also have compounds. When they are formed, they're going to have atoms that are going to combine. They're going to be different types of elements in a compound. And they are always going to have the same relative number of atoms and kinds of atoms. So Dalton's theory was a really good starting point for atomic theory. There are some issues with it. So issues with the John Dalton's atomic theory. One of the big drawbacks of Dalton's atomic theory is that he says that atoms of the same element are all the same in every respect, but that's not true. So atoms of a given element are not all identical. And that's because we have things called isotopes. Isotopes are when we have the same atomic number, so therefore we have the same element, but we have different masses. Right, so they're going to have different masses, and it's because they have different number of neutrons, but they're still the same element. And they also are going to have, because they have different masses, they're generally the same size, so they're going to have different densities as well. So this is not, number 2 in Dalton's atomic theory is not entirely true. And he also said that if we have atoms of different elements, they're going to be different in all respects, and that's also not true. So some atoms of different elements have the same mass. Such as calcium and argon. There are isotopes of calcium and argon that both have the there are isotopes, for instance, argon and calcium. There are isotopes of argon and calcium that both have the same atomic mass of 40 AMU. Another thing that this theory fails to account for is that an atom can be further divided into protons, neutrons, and electrons. So atoms can be broken down into protons, neutrons, and electrons. Okay? So let's look at the components of an atom. Atoms themselves. Atoms are very small. So it makes sense that Dalton's atomic theory didn't have everything right, because you can't really see that. And we're talking about late 1800s, early 1900s that Dalton developed his atomic theory. Atoms are somewhere between 30 and 300 picometers. So even now it's very difficult. Even nowadays it's very difficult to see an atom. But back then it was very hard to see. So everything that, all the theories that existed for the atom back there were based on what they could observe, which not always great. But despite that, the atom itself, the parts of the atom, which are the proton, neutron, electron, were discovered pretty early on. So the proton, which is positively charged, was discovered in 1911. The electron in 1897, and the neutron in 1932. So these components of an atom, the proton, positively charged, electron, negatively charged, and neutron, neutrally charged, were all discovered in the late 1800s, early 1900s, despite the fact that atoms themselves are very small, and subatomic particles, things that are smaller than an atom, are even smaller. Around 1 femtometer in size. Very small. And looking at these dates, you might wonder, how in the world did such small particles get discovered in the 1800s and 1900s? I do want to kind of direct your attention towards what was discovered first, the electrons, a negatively charged particle, and a particle that is one that we would say is pretty easy to remove. The next subatomic particle that was discovered was a proton, which is positively charged. It's not one that can be very easily removed. It's all the way in the center of the atom itself, so it's a very hard particle to remove, but it does have a positive charge, which makes it a little bit easier to discover, which is probably why it was discovered before the neutron, about 21 years before the neutron. Okay. So let's start with the discovery of the electron. It starts with J.J. Thomson, who was working with the cathode ray tube. The cathode ray tube itself is a tube, as seen here, that is evacuated. It has no atoms inside the tube itself, and it's affixed with a cathode and an anode. The cathode is a negatively charged plate, and the anode is a positively charged plate. So the cathode itself produces a stream of negatively charged particles. At this point, it was unknown what these negatively charged particles were, but later they were discovered to be, by J.J. Thomson, to be electrons. So this negative stream of particles was able to be visualized because the cathode ray tube itself had a fluorescent screen wrapped around it, incorporated within the cathode ray tube, and as that stream of negative charge interacted with it, it caused that fluorescent screen to fluoresce, so you'd see the emission of light. So what J.J. Thomson did is he used a magnet and he basically manipulated that stream of negative charge. So when he took the bar magnet and he introduced that stream of negative charge to a positive pole of the magnet, the negative charge would go towards that positive magnet pole. And then if he flipped over the magnet and used the negative pole, he could deflect that negative stream of particles. So what he discovered is, additionally, if he changed the strength of that magnet, he could change the attraction or deflection of the stream. And from here, he discovered that he was actually dealing with electrons. So he adjusted. The strength of the magnet. And discovered that the strength determined the degree of repulsion or attraction of the particles from the cathode. So from this, he calculated the charge to mass ratio of the electron. And he determined it to be 1.76 times 10 to the 8 coulombs over grams. Next major advance in our atomic theory is by Robert Millikan, who is working on an oil drop experiment. In Robert Millikan's oil drop experiment back in 1909, he had the following setup. So he started out with zero field, so there's no applied voltage, and he took an atomizer, this thing right here, which is just a fancy name for a perfume bottle sprayer, filled with oil, and he was able to produce a mist of oil droplets using the atomizer. That mist of oil droplets were then allowed to drop through the hole in the top plate, and then they dropped through the second chamber in individual droplets. After that, he was able to take a source of X-rays and charge each individual oil droplet. And he applied a voltage to the plates. So we had a positively charged plate on the top, negatively charged plate on the bottom. And using the two charged plates, he was able to balance the negatively charged oil droplets in between the two plates. With different size oil droplets, he had to use different amounts of charge on the two plates. But eventually, after many different massed oil droplets and different applied voltages, he was able to come up with a common multiple for each of the mass charge ratios of those oil droplets. And he came up with that, the mass of an electron. And the charge of an electron. So he was able to determine both the mass and charge of an electron. The mass of an electron itself, he determined to be 9.10 times 10 to the negative 28 grams. Just as a point of reference, our currently accepted mass for an electron is 9.10938 times 10 to the negative 28 grams. So very close to the value we got just by balancing charged oil droplets between two charged plates. As I said, he also determined the charge of an electron, and this was a little bit off. But still pretty close. So he determined the charge of an electron to be 1.592 times 10 to the negative 19 coulombs. And our currently accepted value for that is equal to 1.602 times 10 to the negative 19 coulombs. So that would be what we call the electronic charge or elementary charge. But he came very close to that value as well, just again with this simple experiment. Next thing I want to look at before we move on to our next subatomic particle is the idea of radioactivity. So when we're talking about radioactivity, we're talking about the emission of ionizing radiation or particles. So either radiation that's ionizing or particles that are ionizing. And it's caused by the spontaneous decay of an unstable nuclei. Okay. So radiation is defined as emission of energy in the form of electromagnetic rays. As a note, not all radiation is going to be ionizing radiation. And some examples of radiation include light, X-rays, microwaves, radio waves, all sorts of different types of electromagnetic radiation. Also, radiation can be moving subatomic particles. Moving subatomic particles that have been ejected. So such as a ejected electron. Okay, so let's look at some history of radiation. First, 1895, Wilhelm Röntgen discovered X-rays. He discovered them when he observed the fluorescence of a barium salt-coated cardboard screen that was exposed to a cathode ray tube. So he basically determined that there was these invisible rays that were originating from the cathode ray tube, and it was that was causing the fluorescence from that barium salt-coated cardboard screen. He also took this and was the first one to make an X-ray image, and it was of his wife's hand. So using this idea and the photographic plate to make the X-ray of to make an X-ray of his wife's hand. Next, in 1896, we have Antoine Becquerel. And he discovered radiation from uranium. Then in 1911, Marie Curie won the Nobel Prize for the discovery of polonium and radium. She's also one that coined the term radioactivity, and she was the one who verified that uranium did in fact emit radiation. Next, let's look at our types of radiation or radioactivity. So we've got three types: alpha particles, beta particles, and gamma rays. So these are the three that we're going to be investigating today. Our alpha particle is going to basically be a helium nucleus. So it contains 2 protons and 2 neutrons, but no electrons. So this is going to have a charge of +2 and mass of 4 AMU, atomic mass unit. We'll talk about that here soon. So because of its large size and its high charge, a couple of things are a consequence. One, it's going to be the least energetic. It's also going to be the least penetrating because of its large size. But because it has that high charge, it's going to be the most ionizing form of radiation. It will be stopped by a piece of paper or our skin. So, most ionizing because of its large charge, but least energetic and least penetrating because of the large size and charge. So it'd be stopped by a piece of paper. Okay. It would also be stopped by our skin. So usually alpha particles are not very dangerous to the human body. Next form are beta particles. This is a high energy fast moving ejected electron. Okay, so it is a negative charge, so it's negatively charged, although it only has a -1 charge, not a +2 like we see with our alpha particle, and it is much less massive. Because of these factors, it is going to have a smaller, because of these factors, it's going to be less ionizing than alpha particles, but it is more energetic and more penetrating. It would be stopped by aluminum, but it would go through paper. So more energetic and penetrating compared to an alpha particle. But less ionizing. Stopped by aluminum sheet. Last type of radiation I want to talk about is the gamma ray. This is going to be high energy electromagnetic wave. And because we're talking about an electromagnetic wave, this is going to have no charge and no mass. This has several consequences. For instance, it's not going to ionize quite as well because of that lack of charge. So it is the least ionizing of the three types. However, because it doesn't interact with matter, and because it's a high energy wave, it is going to be the most energetic and the most penetrating. So it is a very dangerous form of radiation because of that. Because it's so penetrating, it requires a thick piece of concrete or lead to stop it. But anything less, it will just penetrate and go through. So, J.J. Thomson developed an atomic theory that was dubbed the plum pudding model. And the reason it was dubbed the plum pudding model was due to the way that it looked. So he discovered electrons, and after the discovery of radiation, he developed his plum pudding model. Again, he didn't call it that, but that's what it got named, where he said that an atom is a sea of positive charge with negatively charged electrons distributed throughout. It was called the plum pudding model because it looked like the plum pudding English dessert, where you have pudding with a bunch of little plums dropped throughout. So this is what he proposed the Adams model was. And it was very quickly overturned by Ernest Rutherford and Ernest Marsden using the gold foil experiment. So Ernest Rutherford conducted the gold foil experiment. And then Ernest Marsden was his graduate student who actually probably did all of the work on here. So Ernest Rutherford was actually trying to Ernest Rutherford was testing the plum pudding model using this gold foil experiment. And let me just explain the gold foil experiment real quick. So here is a source of alpha particles. This source of alpha particles were shot. This beam of alpha particles was shot at a gold foil, a very thin piece of gold. And as it was shot at that gold foil, most of the particles went right through. And then they were detected on this circular fluorescent screen. Okay? And that is what they expected. They expected that to happen, that most of them were scattered less than a degree. So most particles, most of those alpha particles were scattered at approximately 1 degree. So not a lot of scattering going on. And that was consistent with the plum pudding model. However, when they looked a little bit further, they found that approximately 1 in 20,000 were scattered at an angle greater than 90 degrees. That was not consistent with the plum pudding model. So from this, what he expected, if the Thomson model was correct, is that very few of those alpha particles would be deflected due to the dispersed positive charge. However, what Rutherford found was that 1 in 20,000 were scattered. And from this, he came up with his own nuclear model, saying that there was a very dense center of positive charge, and the rest of the atom is basically empty space. So with his atomic model, there's a dense positive charge in the center of the atom. But most of the atom is empty space. So at this point, all he really knew is that most of the atom was empty space and that there was a dense positive center. But subsequent experiments led to the discovery of the proton in 1919. So Rutherford did additional experiments and discovered the proton in 1919. Then in 1932, James Chadwick discovered the neutron. That wraps up our history lesson. We're going to look a little bit more at the actual modern view of an atom. So let's summarize the modern view of the atom. The atom has 3 subatomic particles. We have the electron, which has very little mass, and it surrounds the nucleus. So it is not contained within the nucleus. It has a charge of 1.602 times 10 to the negative 28 times 10 to the negative 19 coulombs. And it is negative in nature, so we generally just call it -1. This right here is called the electronic charge. The 1.602 times 10 to the negative 19. Then we have our proton. It is more massive and located within the nucleus. Okay. It also has a charge of 1.602 times 10 to the negative 19, but it's positive. And because they are equal but opposite, we just call them +1 and -1, right? And the proton in the nucleus, while the electrons are constantly in motion around the nucleus. And then our other subatomic particles, the neutron, basically the same mass as the proton. But no charge. And also resides in the nucleus. Okay. So the proton and neutron are both in the nucleus, and the electrons are held to the nucleus by that electrostatic interaction between the positively charged protons and the negatively charged electrons. So the electrons are held to the atom by electrostatic forces. So between positively charged nucleus and negative charge of the electron. Okay, so it's that attraction between the positive and negative that holds the electrons in. Now let's look a little bit more into the forces within nature. Which include that electrostatic interaction, which is why I want to talk about it. So there are 4 basic forces in nature that hold things together or pull them apart. First is gravitational. And this is going to be an attractive force between all objects, but it's proportional to their mass. So atoms themselves are so small that they don't really feel much gravitational force, so we're not really going to look at gravitational. Next is electromagnetic force, electrostatic force. And this one is very important for us. So this is the attractive or repulsive forces between electrically charged particles or magnetic objects. Okay, so this is what holds protons and electrons together. Okay, so it's what causes repulsions between electrons. So it causes electron repulsions. And it causes proton-proton repulsions. Okay, so it's what causes our electrons to be so far apart from each other, which is why so much of our atom is empty space. And these forces are very important in determining chemical properties of an element. Okay. The strength of our electrostatic force is based upon the following equation. Force is equal to this K constant times by Q1 times by Q2, all divided by D squared. So Q1 and Q2 are the charges on the particles, or the strengths of the magnets, and then D2 is the distance between those. So the greater the charges, the smaller the distance, the greater that force. Our next force is the strong nuclear force. And this is a force that holds our nucleus together. Okay, so this is going to be a very strong attractive forces keeping protons within nucleus, so overcoming that repulsion between protons. Okay, it is significantly stronger than electrostatic attractions or repulsions, but it's very short range force. So much stronger, but much shorter distance. So we would say that the electrostatic force is a kind of long-range force, while our strong nuclear force is a very short-range force. And then lastly, we have the weak nuclear force. And this is just another force within the nucleus that is seen within radioactively decaying species. So we are not going to look very much at that. But I wanted you to be aware of all of the different types of forces in nature. Okay, we are going to look at what's called the atomic mass unit and angstrom. So these are units we use specifically for atoms. So our atomic mass unit, AMU, is a unit used for very, very small masses, such as atoms. So atoms have small masses. So a special unit was made just for them. So it's a unit specifically for mass, specifically for atoms. Okay, so 1 AMU is going to be equal to 1.66054 times 10 to the negative 24 grams. If we have a proton, it is going to have a mass of 1.0073 AMU. A neutron has a mass of 1.0087 AMU, so slightly more massive, but not by much. And then an electron has a mass of 5.486 times 10 to the negative 4 AMU, significantly smaller than our proton or neutron. We also have angstroms that is used to measure the diameter of an atom because, again, atoms are very, very small. So the angstrom is a very small length unit for atoms, where 1 angstrom is equal to 1 times 10 to the negative 10 meters. So we should be able to use these units. Let's try an example. So in the following example, we have a silver coin that has a diameter of 17.9 millimeters, and we have the diameter of a silver atom at 2.88 angstroms for each silver atom. Assuming they're arranged side by side across the diameter of the coin, how many silver atoms would that be? We also want to know if the mass of one silver atom is 107.87 AMU, how many femtograms are all of those silver atoms? So first step should be to convert from millimeters into angstroms. So we have 17.9 millimeters. We want to go from millimeters into meters. So for every 1 meter, we have 1,000 meters. So for every 1 meter, we have 1,000 millimeters. And then we want to go from meters into angstroms. For every 1 meter, we have 1 times 10 to the 10 angstroms. And then every silver atom has a diameter of 2.88 angstroms. Take all that, and we get 6.22 times 10 to the 7 silver atoms if they're all arranged side by side. We could then take that number of silver atoms and use the mass of one silver atom to get into AMU. So get our mass of all of those. We now want to go from AMU into grams. So 1 AMU is equal to 1.66054 times 10 to the negative 24 grams. And then once we're in grams, we want to get into femtograms. So 1 gram is equal to 1 times 10 to the 15 femtograms. Multiplying and dividing all of that out, we get 11.1 femtograms. And we should have three significant figures for all of these. Next, we want to look at our atomic number and mass number of an atom. So if we look at the periodic table, our whole periodic table is going to be arranged by atomic number. So Our atomic numbers range between 1 and 118. And each different atomic number has its own element associated with it. So each different atomic number is a different element. The atomic number itself is always a whole number. And it's always a whole number because it equals the number of protons. So our atomic number and our number of protons are equal. So when we say that each element is a different atomic number, and we say that our atomic number is our protons determine what our element is. The number of protons will tell us what element we have. And that will always be true, no matter what. If we have 6 protons, we are always talking about carbon. If we have 1 proton, we are always talking about hydrogen. So the proton is the chemical identifier for an atom. Now, an atom itself has to have the same number of protons to be that atom type, but it does not have to have the same number of neutrons. So we have what's called an isotope, which means we have the same number of protons, but different numbers of neutrons. So, in order to determine what our number of neutrons are, we use what's called the mass number, where the net mass number is number of protons plus number of neutrons. Okay? The electrons themselves are not going to be included in this mass number because they do not have a very large mass. And then we have an element symbol. And this can be written for any element that we know both the atomic number and mass number for. So it shows the atomic number, the element symbol, 1 to 2 letters, and mass number. So it tells us what isotope we're talking about. So let's look a little bit more at isotopes. So again, isotopes, same number of protons, different number of neutrons, and most elements are composed of different isotopes of the same atom. For instance, if we take carbon. Carbon is made up of many different isotopes, but the 4 common ones are carbon 11, carbon 12, carbon 13, and carbon 14. So these are the isotopes of carbon. Each of these isotopes are going to just differ in the number of protons. Each of these isotopes are going to differ in the number of neutrons, so they're all going to have different masses. So on the top up here, these are our mass numbers. And then on the bottom, we have our atomic number. And then, of course, our element symbol. In the case of carbon, it's just a C. So naturally occurring carbon is going to be a mixture of these 4 isotopes in specific amounts, which are based upon the abundance of each of the isotopes. So the amount of each isotope of carbon, or any one, is based on the isotope's natural abundance. Different isotopes are going to be more prevalent or more abundant than others. So, let's do a little recap real quick of our subatomic particles. We're determining the number of subatomic particles. So, if we want to know how many protons and neutrons we have to know our mass number. So our mass number is equal to our number of protons plus our number of neutrons. Okay. We can also determine our number of protons and electrons if we know our charge. Or we can determine our charge if we know our number of protons and electrons. So our charge is going to be equal to our number of protons minus our number of electrons. Last thing I want to talk about is our element's atomic weight. So, when we talk about the atomic weight that we see on the periodic table, it's based on a weighted average of all of the atomic masses. So weighted in that each isotope has different abundances, and those abundances are taken into account when we determine the atomic weight. So the atomic weight of an element is determined by taking the sum of all of the isotope masses multiplied by their fractional abundance. So let's look at an example of our isotopic abundances. So we have chlorine, and chlorine-35 is 75.78% abundant, and it has an atomic mass of 34.969 AMU. We also have chlorine-37 at 24.22%, which has an atomic mass of 36.966 AMU. We want to know from this information what our atomic weight is. Let's solve for the atomic weight here. For our atomic weight, we're going to take each of the isotopes, take their masses, and multiply by their fractional abundances. To get to the fractional abundance from the percent abundance, which is what's shown in the problem, we just divide our percent abundance by 100. So we'll take our first isotope, number 35, its fractional abundance, 0.7578, and multiply it by the mass of 34.969 AMU. And then we're going to add that to our other isotope with its fractional abundance of 0.2422 multiplied by its atomic mass, 36.966 AMU. So what we get is 26.4995 AMU plus 8.9532 AMU. Now, we do need to consider significant figures. This should have 4 sig figs. This should also have 4 sig figs. So each one of these should have 4 sig figs. So we're actually have 26.50 AMU plus 8.953 AMU. And what we get is 35.453 AMU. So now we again have to consider sig figs. Addition is number of decimals. This one has 2. This one has 3. So our answer should have 2, which gives us an answer of 35.45 AMU with correct number of sig figs. That is everything I have for you guys today. I will talk to you guys in the next one.